Hello, everyone. My name is Anton Bernshteyn, and in this talk, I would like to tell you about recently discovered connections between distributed computing and a seemingly rather different area of math, namely descriptive combinatorics. And to begin with, I should tell you a bit about what descriptive combinatorics is. This is a subject that emerged in the last 20 or 25 years out of the interactions between combinatorics, and especially graph theory on the one hand, and a field called descriptive set theory on the other hand. And there are some nice surveys by Kekris and Marks and Pehurko that you can look up. So to motivate the sort of questions that we ask in descriptive set theory, I would like to draw some parallels to computational complexity, which is a subject that is probably familiar to most of you. So computational complexity provides a general framework for studying the difficulty of mathematical problems. And it's really versatile. The problems can be of any nature. They can come from graph theory, number theory, algebra, really any field of math. The only restriction is that they have to be finite problems somehow, so that the tools of computational complexity theory can apply to them. And you can think of descriptive set theory as taking one step further and building a similar framework for studying problems in the countable setting. So how does that work? One way to describe it is by introducing an infinite computational model. And here's a very simple one, countable Boolean circuits. So what is a countable Boolean circuit? Is a diagram that looks like this one here, for example, which is, so it's a directed network where on the bottom layer here we have input nodes, each of which represents an input bit. It's either 0 or 1. And then we have logic gates, say OR gates or AND gates or NOT gates, right? And each of them takes in some inputs from the previous nodes and computes the corresponding Boolean function of them. So for instance, this gate here computes the OR of all of the inputs. And this one here computes the AND of all of the OR gates here on the second layer, etc. And then at the end, there are some of the gates just produce the output of the function. So this is very similar to finite Boolean circuits, except that this diagram is allowed to be infinite, but only countably infinite. So in particular, the inputs here are not finitely many bits, but we feed into the circuit an infinite string of zeros and ones. And also, there can be infinitely many gates, like here there are infinitely many OR gates on the second level. And each gate, each of these OR or AND gates can have countable fan-in. So there can be countably many inputs sent into each of them. So one technical issue I should point out is that in the finite setting, when we define finite Boolean circuits, we require this network to be acyclic. And this is because if you have a cycle, a directed cycle among the gates, then it represents some kind of circular dependency between them. So we cannot actually evaluate them because of that. In the infinite setting, in addition to saying that there are no cycles, we also have to say that there are no infinite descending sequences of gates. So what I mean is that there shouldn't be a gate G0 that depends on some gate G1, which depends on G2, which depends on G3, etc. Because the computation has to start somewhere, right? If there is such an infinite sequence of dependencies between the gates, then we cannot actually evaluate them because there is nowhere we can start. It doesn't reduce to the inputs. So a circuit that doesn't have cycles and doesn't have such infinite descending sequences is called well-founded. And so that is the right requirement for infinite circuits, that they have to be well-founded. Well, this circuit here in this picture, for example, is well-founded. It's not hard to check. But other than this difference that they have to be well-founded instead of acyclic, the rest of the theories is very similar. So given such a circuit, and on every input, it evaluates to produces some output value. And what we want to understand is what can be computed in this model. And you can think of these circuits somehow as providing an explicit model for what it means to compute something in having countable computational resources somehow. So that's what we want to understand. What can be computed if we have countable computational resources? So formally, we'll look at the set of all, this is 0, 1 to the n. This is the set of all infinite strings of bits. And we say that the subset A there is Borel if its characteristic function can be computed by a countable Boolean circuit. So there is a circuit that, given an infinite bit string, decides whether or not it belongs to A. And we let this curly B of 0, 1 to the n denote the family of all Borel subsets in 0, 1 to the n. So let's look at some examples. And as usual, the definition is given in terms of infinite sequences of bits, but the point is that all sorts of other objects can be encoded by infinite bit strings. For example, suppose you want to study countable graphs. So a graph G on a countable vertex set V can be represented just by its adjacency matrix. It's going to be an infinite matrix in this case because the graph is infinite. But still, it's an infinite matrix. So in row I and column J, there is a 1 if Vi is adjacent to Vj and 0 otherwise. Now, if you represent a graph by such an adjacency matrix, you can run countable Boolean circuits on this input. So you can feed it into a countable Boolean circuit and see what it produces. So we can talk about Borel sets of countable graphs. And for example, the following sets end up being Borel. Say the set of all connected graphs. And so again, saying that this is Borel means that somehow there is a countable procedure, if you like, that given a adjacency matrix of a graph G, decides whether or not it's connected. And essentially the way it works is you have to check for every pair of vertices whether or not there is a path between them. And this can be done by a countable Boolean circuit. Here's another example. We can check whether a graph is a tree. So we need to check whether it's connected, and also whether or not there is a cycle in it, which somehow also can be done. The set of all bipartite graphs is Borel. This is the easiest way to see this is that that's because a graph is bipartite if and only if it doesn't have odd cycles. Somehow, given an adjacent matrix of a graph, it's not hard to check whether or not there are odd cycles there. Maybe a bit more surprisingly, especially in view of the parallels with the computational complexity, the set of all 3 colorable graphs is also Borel, as it turns out. So somehow the 3 colorability 3 coloring problem is easy in this sense in the countable realm. The reason for this is that a graph is 3 colorable if and only if every finite subgraph of it is 3 colorable, and somehow that is possible to check using a countable Boolean circuit again. On the other hand, here's an example of a set that is not Borel, so that actually is genuinely more complicated than these ones. Which is the set of all graphs that have an infinite clique. So you can prove that there is no countable procedure that, given a countable graph, decides whether or not there is an infinite clique in it. Okay, so there is a way of thinking about Borel sets that's more general than this. So far I've described Borel sets in terms of the specific computational procedure. There is a more sort of robust way of defining them that isn't connected to a specific model of computation. And in order to explain this, I need to put a metric on the space of all infinite bit strings. So I'm going to say that the distance between x and y is, well, what I want to do is take some sort of Hamming distance. I want to just see how many positions x and y differ. The problem is that because x and y are infinite strings, there can be infinitely many places where they're different, but I want the distance to always be finite. And because of this, we normalize it in this way by, say, multiplying the difference in the ith coordinate by 1 over 2 to the I plus 1. So in this way, even if x and y are different in every single coordinate, this will evaluate to 1. So this is sort of normalized Hamming distance on 0, 1 to the n. And now with this metric, this becomes a metric space, so we can use topological terminology. We can talk about open subsets of 0, 1 to the n, closed subsets, things like that. And it turns out that every open subset of 0, 1 to the n is Borel, and moreover, so its characteristic function can be computed by countable Boolean circuit, and moreover, the Borel sets really are generated by open sets in the following sense. That the family of all the Borel subsets of 0, 1 to the n is the smallest collection of subsets that includes all open sets. and also is closed under countable Boolean operations, meaning countable unions, countable intersections, and complements. Yeah, so this doesn't directly reference this particular computational model somehow. Just says that this is the smallest family of subsets with these properties. And what's nice about this, if you take this as a definition of a Borel set, then this doesn't actually use that the points in my space are sequences of bits, right? The only thing we need to know is what are the open sets. We have to have a notion of an open set. So this really works for every topological space. We can generalize this by saying that just defining a subset of a topological space X to be Borel, if it belongs to the smallest family of sets that includes all open sets and is closed under countable Boolean operations. So this definition works for every topological space, but in descriptive set theory, we focus on a special class of topological spaces, so-called Polish spaces. And you don't worry about how exactly this is defined. The definition will not be relevant for the rest of the talk. But roughly speaking, the reason why we study Polish spaces specifically is because points in the Polish space can be encoded by infinite bit strings in some kind of nice or well-behaved manner. So that's the idea. So really, you can translate questions about Borel sets in the Polish space into questions about Borel sets of infinite bit strings, and that is why we like Polish spaces. So here's some examples. Well, 0, 1 to the n itself, that's a Polish space. This is maybe our prototypical example. But also say the set of all real numbers. And how do you encode a real number as an infinite bit string? Well, you write it out in binary or something like that. And so in this way, you can really kind of apply this theory of countable computation to points in R. And okay, R happens to be a Polish space according to this topological definition. And similarly, instead of just the real numbers, you can consider n-dimensional space Rn, or even infinite dimensional space. This is the space of all infinite strings of real numbers, or this n to the n, the space of all infinite sequences of natural numbers, or all sorts of subspaces in these, like the closed unit interval, open interval, n-dimensional spheres, etc. So kind of any sort of nice geometric space that you can think of is very likely to be Polish. But in addition to these geometric examples, there are more. Remember, thinking about these parallels with computational complexity, we want this to be a versatile framework that we can use to study complexity of problems arising in different parts of mathematics. And for this, really, we just need to be able to encode the objects that we are studying by infinite bit strings. So for instance, we already saw how to encode a countable graph by looking at its adjacency matrix. And in this way, you can form a space of countable graphs. So you can talk about Borel sets of countable graphs. But you consider all sorts of other structures, not graphs, but say countable groups, for example, can be encoded in a similar way. There is a Polish space of the Polish spaces of continuous functions or measure preserving transformations, separable Banach spaces, etc., etc. You know, any well, not literally any, but lots of objects that people study in mathematics. If somehow you can encode your infinite structure by an infinite string of bits, then that suffices to put it into this framework. Okay. So let's review the types of constraints that we study in descriptive set theory. So let's go back for a second to just 0, 1 to the n infinite bit strings. So given a subset there, remember we said that A is Borel if the membership in A can be decided by a countable Boolean circuit. In addition to this, there are different other notions that we can consider. For example, we know that open sets are Borel, so maybe we just want A to be open. And this is a topological notion, but in the case of the space of these infinite bit strings, it turns out to be equivalent to the following purely combinatorial notion. So a set is Borel if the following is true, that for every point x that is in A, it is possible to prove that x is in A by only revealing finitely many entries of x. So x is an infinite bit string, but actually if I want to convince you that x is in A, I just need to show you finitely many entries of x. And this condition turns out to be equivalent to saying that A is open. So this topological terminology really somehow equivalent to very combinatorial notions. And this is stronger than being Borel. On the other hand, a lot of the time, what we really want to consider is notions that are weaker, some kind of relaxations of Borelness, because Borel maybe is too hard to achieve. For example, we can talk about sets that are measurable. One way to define a measurable set in this context is to say that there is a countable Boolean circuit, C, that maybe fails to correctly decide whether an input string X is in A. Sometimes, so in the Borel setting, you just always give it an input, it says either this is an A or this is not an A, and it's always correct. In the measurable setting, the circuit can sometimes be wrong about whether X is an A or not. But if you feed into it a random input, so if you flip a coin countably many times, you produce an infinite string of zeros and ones, and you put it into the circuit C, then the probability that it incorrectly classifies X is 0. In other words, with probability 1, C is going to correctly tell you whether this random input was in A or not. Which of course, this is a weaker condition than A being a Borel set, because in the Borel case, really for every single input, the circuit has to produce the correct output. But for many applications, this is sufficient. Somehow, maybe we only care about what, we don't care about what happens on the set of measure 0, right? What happens with probability 0. And so then it's enough for a set to be measurable. So we can make our life easier in this way. There is another notion I should mention, which is A being bare measurable. I will not define this precisely, but you should think of it as just a topological version of measurability. So instead of using probability here to say that a circuit fails with, most of the time because the probability that it fails is 0, here we just use the topology on our space to somehow define a topological notion of smallness. So a set is bare measurable if there is a countable Boolean circuit C such that if you look at all the strings of bits for which the circuit fails to correctly determine whether it's in A or not, this set is what is called meager, and that I'm not going to define this precisely, but that somehow means that it's topologically small. So instead of saying that the set is of measure 0, which is how you define measurable sets, you say that it's meager. And that means small in some kind of topological sense. Okay, so these are the 4 main notions that we study. These definitions, the way I wrote them, apply to sets of bit strings, infinite bit strings, but they make just as much sense for subsets of arbitrary Polish spaces. Yeah, so again, we can talk about Borel sets, and sometimes we even talk about open sets, which is more restrictive, and sometimes we look at less restrictive sets, which are less restrictive notions, which are measurability or bare measurability, where the first one means that it's Borel except for a probability 0 event, and the second means that it's Borel except for a meager event, which is somehow small in topological sense. Okay, so this was descriptive set theory in general. In descriptive combinatorics, we apply these ideas to combinatorial problems or graph theoretic problems, especially. And the key notion for us here is the notion of a Borel graph, which is a graph G such that the vertex set of G is a Polish space. So somehow it puts it into this descriptive set theory framework. And the edge set is a Borel subset of the product space, V of G cross V of G. What this means is that there is a kind of countable procedure, countable Boolean circuit or something like this, that given 2 vertices X and Y decides whether or not X and Y are adjacent in G. So for example, here's an example of a Borel graph. Let's call it H. The vertex set of H is going to be, again, our favorite, 0, 1 to the n, the set of all infinite bit strings. And I'm going to put an edge between the vertex X and the vertex Y, if and only if X and Y differ in precisely 1 coordinate. So X and Y are infinite sequences of zeros and ones. And if they differ in exactly 1 coordinate, then we put an edge between them. So it's like an infinite dimensional analog of the Boolean cube. And this is a Borel graph. What this means is simply that if given 2 infinite sequences of zeros and ones, there is some kind of countable procedure that decides whether or not there is an edge between them. And you can imagine how this is going to go, right? You need to check for every, you can see for every I whether xi is equal to yi, and then you need to see that there is precisely 1 place where they're different. It's not hard to encode this idea as a countable Boolean circuit. So I should point out that there is something different between this infinite dimensional Boolean cube and the finite dimensional analogs. Namely, the graph H is disconnected. Not only is it disconnected, it actually has uncountably many connected components. The reason is that if we start with a vertex X, right, if you follow a path from some vertex, well, when you take a step along an edge, you can only change the value of one coordinate. So in finitely many steps, you can only change finitely many coordinates, which means that the only vertices that can be reached from X, from a sequence X, are those which differ from X in only finitely many places. In particular, for example, if the sequence that's all zeros and the sequence that's all ones, they belong to different connected components of H. And in fact, there are uncountably many connected components in this graph. So it's very much disconnected. On the other hand, there are still some properties that it does inherit from finite dimensional Boolean circuits. For instance, it's bipartite. The easiest way to notice this is by observing that it cannot contain an odd cycle. Because if you start with the vertex, you go along the cycle, you return back. Each time you change exactly one coordinate, and if you return back, you have to change every coordinate an even number of times. So the cycle has to be of even length. And so what does this mean? The graph is bipartite. It means that we can color the vertices, say red and blue, so that adjacent vertices always receive different colors. But now our vertices are these infinite bit strings, so we can ask whether or not we can compute a coloring with two colors using a countable Boolean circuit, right? And turns out that the answer is no. Even though the graph is bipartite, there is no Borel two coloring. In other words, there is no way, there is no two coloring that is computable by a countable Boolean circuit. Even more is true, actually. There isn't even a Borel coloring using countably many colors. Even if you increase the number of colors, it's not two, it's not even finite, countably infinite. There is no Borel function that assigns to every vertex in our graph a natural number such that f of x is not equal to f of y when x is adjacent to y. And the way we express this fact in descriptive combinatorics is by saying that the Borel chromatic number of H is uncountable. So this is a graph that's bipartite, but if we want the coloring to be Borel, then even countably many colors are not enough. And similarly, instead of Borel chromatic numbers, we can look at measurable or bare measurable chromatic numbers. In this case, they're also uncountable. Okay. So this is the typical descriptive combinatorics result. Let's see one more example of a slightly different flavor. Fix a real number alpha such that alpha over pi is irrational. You will see in a minute why I want alpha over pi to be irrational. And let's define a corresponding graph G sub alpha as follows. The vertex set is just going to be the unit circle. So every point on the circle is a vertex of this graph. And I'm going to put an edge between the vertex x and the vertex y if y is obtained from x by rotating the circle by an angle alpha. So in this graph, every vertex has exactly two neighbors because you can rotate it by alpha clockwise or counterclockwise. These are the two neighbors of the vertex. And if I take a vertex, I rotate it by alpha, then I rotate it again and again and again, right? I produce this sequence of neighbors of each other. And here's where we use that alpha over pi is irrational. This condition ensures that after finitely many steps, we will never return back to the point where we started. So really, every connected component of this graph is an infinite path, infinite in both directions, right? So if I start at this point, I can rotate, say, clockwise to get this neighbor, again clockwise, get this neighbor, etc., or I can go counterclockwise and then I go in the other direction. So every connected component of this graph is this infinite path. It looks very simple. So again, there are uncountably many components in this graph. Every connected component is countable, and there are uncountably many vertices because every point on the circle is a vertex. But every individual component looks very simple. So really, the graph is just there are uncountably many copies of this infinite path, and then somehow put together into this graph so that the vertex set becomes a unit circle. Again, this graph is also bipartite, like the graph in our previous example. It's easy to color a path with two colors, right? And there are no cycles in this graph. So it's again bipartite, but again, there is no Borel or measurable or bare measurable to coloring. And it turns out that the Borel chromatic number, measurable chromatic number, and bare measurable chromatic number of this graph, they're all equal to 3. So in the previous example, the graph was bipartite, but the Borel measurable and bare measurable chromatic numbers were uncountable. In this case, they're still finite, but they're equal to 3, not 2. Okay. So what we want to understand is in general, how difficult it is to solve various combinatorial problems on these Borel graphs if we require the solution to be, say, Borel or measurable or bare measurable. And to understand this really general problem, we need, well, a really general setup, we need to have a formal notion of what we mean by a coloring problem or combinatorial problem on these graphs. So the notion that we're going to look at are so-called locally checkable labeling problems, or LCL problems for short. And what such a problem does is, given a graph G, the task is to assign labels to the vertices. There's a finite set of labels, say integers 1 through k. We need to assign labels to the vertices of the graph in a way that satisfies certain constraints. And the constraints are local, or locally checkable, meaning that given such a labeling, to see that it actually solves the problem, we need to just check whether it satisfies some conditions on constant radius balls around every vertex, on a constant radius ball around every vertex. So, for example, the k coloring problem is a locally checkable labeling problem, right? To see that what is a k coloring problem? You need to assign colors to the vertices so that adjacent vertices get different colors. So you need to check for every vertex whether its color is different from the colors of its neighbors. So you just need to look at a ball of radius 1 around this vertex in the graph. And similarly, something like matching can also be viewed as at least on bounded degree graphs, can be viewed as a locally checkable labeling problem. Here, the label of a vertex encodes, it just tells which of its neighbors it is matched to. And the condition, I guess, is that if x is matched to y should be matched to x. This is, again, something local. It's something happening in just the neighborhood of a vertex. And other examples, like the maximal independent set problem, is an LCL problem, etc. You can think of lots of examples. So we ask a general question now with this notion. We're given a class of Borel graphs, say G, which LCL problems admit Borel or measurable, etc. solutions on graphs from this class. This is a general classification question. We want to classify LCL problems according to their descriptive set theoretic complexity on graphs from some given class. And here is where the connections with distributed computing show up. It turns out that the answer to this classification question is intimately related to the distributed complexity of this problem. In other words, how hard it is to solve this problem on a suitable class of finite graphs by a distributed algorithm. So at this point, now let's change gears for a second. Let's review the model of distributed computations that we're going to look at, which is the local model. I would imagine it's familiar to most of you, but let me still say a few words about it, just to remind you what it is, and maybe highlight some of the aspects of it that will be important. So it's distributed computation. So let's go back to the finite world for a second. We are operating on some finite network, and we think of every vertex as a processor and edges in the network of communication links. And we still want to solve some kind of LCL problem. So for instance, maybe 3 coloring or something. So when you color the vertices, the adjacent vertices get different colors. And we think of every node as in this network as representing an autonomous agent that has to decide what its own, every vertex has to decide what its own label is going to be. The problem is that it doesn't actually know what the graph looks like. It only has the access to its neighbors, and it doesn't know what the rest of the network looks like. And it can send messages to the neighbors and receive messages from the neighbors. And what we want to do is so there are these communication rounds where messages are being passed through the network, and we want to minimize the number of communication rounds that they need to solve the problem. Let me say this one more time. So there's this local model of distributed computation. We operate on an n vertex graph G. And computation proceeds in rounds, where on each round the vertices first perform arbitrary local computations and then send messages to their neighbors. And these local computations can be arbitrarily complex. We imagine that the vertices have unlimited computational power. And the messages, we also don't care how long they are. They can be arbitrarily long. And after some number of rounds, each vertex has to decide on its own part of the solution to the problem. So since you're in this LCL problem setting, it has to decide what its label is going to be. And the complexity of such an algorithm is measured by the number of rounds required. So that's the only parameter we're concerned with. The important feature of this setting is that every vertex in the graph executes the same algorithm. So it doesn't know where in the graph it is initially, and it has to execute the same algorithm, which means that we need some ways of breaking symmetry between the vertices. Otherwise, without any symmetry breaking baked into the model, there's very little that actually can be computed. There are two standard variants of the model depending on what symmetry breaking methods are used. Deterministic version of the local model, each vertex is just given a unique identifier. So part of the input for every vertex is a number. Say you can think of identifiers as just a number between 1 and n, and they're all guaranteed to be different. But initially the vertex knows just its own identifier. It can tell the neighbors in the first round. It can tell its neighbors what its identifier is, right? And it can learn the identifiers of its neighbors, etc. But yeah, but it's guaranteed that the identifiers are all different from each other. And this is the deterministic version. So regardless of how the identifiers are assigned to the vertices, the algorithm has to produce a correct solution to the problem. There is also the randomized version of the local model, where instead of the identifiers, each vertex is given a random number generator, so it can produce an arbitrarily long sequence of independent, uniformly distributed random bits. And since this is a randomized model, we don't require the algorithm to succeed always. It just has to succeed with probability very close to 1, say greater than 1 minus 1 over n, where n is the number of vertices in the graph. Okay. So why is this called the local model? Another often more useful way of thinking about it is that, well, think about it this way. In one round, the vertex can communicate only with its neighbors, and then they next round they can send the information to their neighbors and etc. So information can travel one step at a time in the graph. So in t rounds, a vertex only can learn about what is happening in the radius t neighborhood of this vertex. It has absolutely no access to what happens outside of this radius t ball around x in the graph. And so if the algorithm succeeds, runs for t steps and then terminates, then after these t steps, the vertex x has to make a decision what its label or its color is going to be, based only on the information contained in this radius t ball. So on the structure of the graph there, and also on the either the identifiers in the deterministic setting or these random bit strings in the randomized setting assigned to the vertices here. So you can really think of a local algorithm as just a function that takes as input these radius t balls around each vertex and produces the corresponding label for every vertex based on that information. In particular, every problem can be trivially solved in the number of rounds that's big O of the diameter of the graph. You can think of it as because in this many rounds, every vertex can learn the entire structure of the graph. So the locality of the problem isn't important anymore. So we want the number of rounds to be small enough so it makes sense to expect it to be significantly less than the diameter. There are some standard benchmarks. We often talk about polylogarithmic algorithms, so those that require polylog n rounds. Maybe you can ask them for big O of log n, or even somehow really truly local little O of log n. So this means that, say, on graphs of, say, bounded degree, right, this is guaranteed to be less than the diameter of the graph somehow. But these are some benchmarks, but these are not the only ones. So let me just give you some examples of what what this model can and cannot do. Say, let's consider a specific case where we're trying to color graphs of maximum degree delta, when I think delta is a constant. So fix a constant delta. We want to find colorings of graphs of maximum degree delta, and then in this setting there is an old result of Goldberg, Plotkin, and Shannon that shows that there exists a deterministic local algorithm for delta plus 1 coloring graphs of maximum degree delta that runs in big O of log star n rounds. The log star n is the iterated logarithm, so it's a very, very slow growing function. So this is delta plus 1 coloring. On the other hand, it turns out that if you want to reduce the number of colors just by one to make it so to produce a delta coloring of a graph, then it's impossible to do with a deterministic algorithm in little of log n rounds, even if the graph is acyclic. So a tree, in other words. Even on trees of maximum degree delta, there is no little of log n round deterministic local algorithm for delta coloring. However, the situation really changes if instead of deterministic algorithms, we consider randomized ones. It turns out that in the randomized setting, for delta at least 3, there exists a, well, big O of log n squared, but really what's important for me here is that this is little O of log n. So it's a little O of log n round randomized local algorithm, the for delta coloring graphs of max degree delta, that as long as they don't have a delta plus 1 clique. Of course, if a graph contains a clique on delta plus 1 vertices, it's impossible to color it with delta colors. So if it doesn't have a clique on delta plus 1 vertices, then it can be colored with delta colors by a very efficient randomized algorithm, but not a deterministic one. And now let's compare it to this slide, which runs parallel to what's happening there. These are some results from descriptive combinatorics. Again, we fix a constant delta, and let's look at a Borel graph G of maximum degree delta. By a theorem of Kekra-Seletsky and Todorchevich, the Borel chromatic number of G is at most delta plus 1. So there is a Borel delta plus 1 coloring of G. On the other hand, Marx showed that there are acyclic graphs G of maximum degree delta, whose Borel chromatic number is equal to delta plus 1, meaning that there is no Borel coloring with delta colors. On the other hand, if we relax the condition requirement from the coloring being Borel to be measurable, so it should only work on a measure 1 set, and you know, it has to work with probability 1. If you like, right? Then, and the graph doesn't contain a delta plus 1 clique, then its measurable chromatic number is at most delta. And also the bare measurable, this topological analog, is also at most delta. So it has a measurable, bare measurable delta coloring, but maybe the graph could even be acyclic and still not have a Borel delta coloring. But there is also a Borel always a Borel delta plus 1 coloring. And if you compare these two, I mean, they're exactly parallel to each other. If you replace the word deterministic by the word Borel and the word randomized by the word measurable or bare measurable. This is exactly the same situation. And is this a coincidence? Well, I would like to convince you that no, it's not a coincidence. There are these parallels are due to the fact that there are some very deep connections between distributed algorithms and these descriptive combinatorics results. And oftentimes you can translate results from one area to the other. So one setting in which this is true is that we know that in a very broad range of cases, efficient distributed algorithms yield results in descriptive combinatorics. So if you want to go from distributed computing to descriptive combinatorics, this is pretty much always possible. So let me describe the setup a bit more precisely. Fix a class of finite graphs, G, with this technical assumption that is closed under writing isolated vertices. So, for example, it could be graphs of maximum degree at most delta, acyclic graphs, graphs without a delta plus 1 clique, you know, things like that, planar graphs. And let G be a Borel graph of bounded maximum degree whose finite induced subgraphs belong to this class. So, for instance, if G is a class of acyclic graphs of maximum degree at most delta, then this just means that G is also an acyclic graph of maximum degree at most delta. Okay, and let pi be some LCL problem. So then it turns out that deterministic local algorithms imply Borel solutions, and randomized local algorithms imply measurable and bare measurable solutions. So more precisely, if the problem pi can be solved on graphs in this class G by a little of log n round deterministic local algorithm, then there is a Borel solution to pi on this Borel graph G. And similarly, if instead the problem can be solved by a little of log n round randomized local algorithm, then on the Borel graph G, it can be solved both in a measurable and bare measurable way. Okay, and so this explains at least some directions between these two slides, right? You see here, we know that there is a big O of log star n round deterministic algorithm for delta plus 1 Calvin graphs of max degree delta. This implies that the Borel chromatic number of a Borel graph of maximum degree delta is at most delta plus 1. So this algorithm here implies this Borel result. And similarly, this randomized algorithm here is again runs in little O of log n rounds. So it implies these measurable and then bare measurable bounds over here. And conversely, the theorem of Marx for acyclic graphs implies the lower bound in this setting, right? Since we know that this graph doesn't have a Borel delta coloring, this means that there cannot be a deterministic algorithm for delta coloring that would work on acyclic graphs of maximum degree delta. Okay, so yeah, again, the consequence is you can go two ways. If you know that there is a fast local algorithm for some problem, this implies that depending on whether it's deterministic or randomized, you can get Borel or measurable solutions to problems on Borel graphs. So in the same paper where these results are proved, I showed it as a sample of such applications. For instance, you can use existing randomized algorithms in the distributed computing world to obtain optimal upper bounds on measurable chromatic numbers of acyclic graphs of bounded maximum degree. You can show that measurable chromatic number is equal to ordinary chromatic number for graphs whose chromatic number is sufficiently close to the maximum degree, things like that. So you can translate results from the local algorithms world to the Borel or measurable setting. And this is very useful because somehow we have, it's general, it seems that, because I guess thinking about finite graphs is easier than working in this infinite setting. We seem to have just more tools at our disposal in the distributed computing world than in the measurable or Borel setting. But on the other hand, you can also go the other way. You can say, well, if I can prove a lower bound, if I can prove that there isn't a Borel or measurable coloring in some setting, this would imply a lower bound for the distributed algorithm complexity of the same problem. And there's been some exciting recent work by this group of authors who used this direction, and they designed a new way of proving lower bounds for deterministic local algorithms on trees using a modification of something that's called the Borel determinacy technique, which was invented by Marx to prove that certain combinatorial problems on trees cannot be solved in a Borel way. And so this technique inspired new methods in deterministic local complexity and produced new lower bounds. Yeah, let me say a couple words about the proofs of these results, these implications. Say this one is not too difficult. So here you're assuming that the problem can be solved by a little log n round deterministic algorithm, say A, and then we want to find a Borel solution to the problem on this infinite Borel graph G. And the argument relies on a technique or some modification of the technique developed by Chang, Kopelowitz, and Petty, that they used it to show that this very interesting gap in distributed complexity of LCL problems. They show that no LCL problem has deterministic local complexity that is strictly greater than log star n, but strictly lower than log n. So somehow there is a gap. If it's little o of log n, it's actually big O of log star n. And the idea of their argument was to somehow have an algorithm that runs on some small graph, and then you have a much bigger graph, and you try to run the same algorithm there. And in terms of the size of the big graph, the algorithm is much faster. So that is the sort of thing that we're trying to do here. We know that the problem can be solved by an efficient algorithm on finite graphs, and we want instead to find a Borel solution on an infinite graph G. So how are we going to do this? Well, we're going to take large but finite integer n, and let t be a running time of this algorithm on n vertex graphs. And by our assumption, it's little o of log n. So we want to run this algorithm on our graph G. right? And since it's a deterministic algorithm, what does it need? It needs, for every vertex in the graph, needs to have a unique identifier. Remember, right? This is the setup for deterministic local algorithms. Of course, we cannot really give unique identifiers that there should be integers between 1 and n, right, to all the vertices in our graph G, because G is infinite. But the key observation is that because of the locality condition, they don't really have to be unique in the whole graph, because the algorithm runs only for t steps. And in this time, a vertex can only see what happens in the ball of radius t around itself. So it just needs to be, its identifier just needs to be, the identifiers just need to be unique in that ball. So we give to each vertex a fake ID and number ID of x, which is just number between 1 and n, so that is unique locally. So if two vertices are at distance less than t plus maybe a constant from each other, then their IDs are distinct. And one can show that this can be achieved in the Borel way. So this now is a specific combinatorial problem. If we can show this in the Borel way, we get a, which we can, then we get a Borel assignment of IDs like this. And now we can run, somehow simulate the algorithm. We run it using these fake identifiers for the vertices. So this is roughly the sketch of how the proof goes for this. This is the deterministic setting. The randomized part, where we have a randomized algorithm that runs in little log n rounds, and we want to find measurable or bare measurable solutions. This is much more involved. I will not go into too much detail about this proof just because it's much more complicated. But I should say that there is I think there's a nice feature of the argument. The key tool that is used is at some point we need a measurable or bare measurable, depending on the context, version of the lowest local lemma to achieve this. And so we need to prove this. And the proof of the measurable local lemma again uses local algorithms. So there is a randomized local algorithm for the lowest local lemma that runs as little of log n rounds due to Fisher and Ghafari. And it has been improved. The running time has been improved after that. But the only thing we need is that it's little of log n. And so we cannot really directly use this theorem to turn this into a measurable version of the local lemma, because the proof of the theorem uses the measurable version of the local lemma. But still, the proof of the measurable version of the local lemma somehow invokes this algorithm, in fact, sort of in iterative way. So there is this really interesting interconnection between somehow the distributed algorithms are really very essential for this whole argument. It's kind of interesting. Okay, so what do we know now? So this is a very general fact that, or I guess a pair of facts that tell us that distributed algorithms can be turned into descriptive results. Deterministic algorithms give Borel results. Randomized algorithms give measurable results, and bare measurable as well. Well, what's really interesting to know is when can we go back from descriptive world to distributed algorithms? In other words, are there really some equivalencies between problems in distributed computing and descriptive combinatorics? And it turns out that there's, so this is mostly open for this other direction. In most cases, the answer is we don't know what is going on, or how to go back, or when we can and cannot go back. But there are a few situations in which we actually do know that descriptive results can be turned into distributed algorithms. So I'm going to describe two settings in which we can go the other way now. So one setting is that of continuous combinatorics. That one we understand really well at this point. So this is, remember I earlier said that, well, you can talk about Borel sets, you can talk about measurable, bare measurable sets, but on the other hand, you can make the conditions more restrictive. Instead of Borel, you can require working with open sets. In other words, you can, instead of asking for coloring to be Borel, so every color class is Borel, you can ask for it to be continuous, which just means that every color class should be open, but because there are finitely many of them, it also means that it should be closed at the same time, because it's a complement of the rest of the color classes. So saying that the coloring or labeling of the vertices of your graph is continuous, it just means that every color class is simultaneously a closed and an open set, or clopen for short. And if you think of, so this puts some kind of restrictions on what sort of Polish space the vertex set of the graph can be, because say the real numbers, if the vertex set of G is the real numbers, there are only two Clopin subsets, the empty set and the whole space. And there's nothing interesting that can be done. There is no interesting continuous combinatorics in that setting. However, so when studying continuous coloring, so continuous solutions to LCL problems, we need to assume that there actually are enough Clopin sets to go around, so that something non-trivial can be done with them. So the assumption that we make usually is that the topology in the space is zero-dimensional, which just means that the topology is generated by Clopin sets. So there are, in other words, there are a lot of Clopin sets to use. And so a typical example, say the space, the 0, 1 to the n, this is a zero-dimensional space. So they're not as uncommon as you might think. They're not these nice geometric objects maybe, but something like 0, 1 to the n. Another example is the reals minus the rationals. So if you remove every rational point from R, so it's just countably many points, if you remove them, the rest becomes zero-dimensional. So really, it's not hard to make a space zero-dimensional. So it's not too uncommon. And in this zero setting, we can define continuous chromatic numbers, for example, chi sub c of g, right? This is how many colors do you need to color the graph, so that the color classes are not just Borel, but actually these Clopin sets. And similarly, we can talk about continuous solutions to arbitrary LCL problems. Okay, so and it turns out that this continuous setting really has some equivalent interpretation in terms of distributed algorithms. But to explain this, I need to describe a specific class of graphs that we might be interested in studying. So you want to study some graphs that are, kind of nice and symmetric, like maybe paths or grids or trees, things like that. And a nice general setting in which we can put this in the setting of these gamma graphs. So how's this defined? We start with a group, a countable group gamma that is generated by a finite set S. I'm going to assume that S is symmetric, which just means that for every generator, its inverse is also in S. And then the Kelly graph of the group of the group gamma is the graph where the vertices are the elements of the group, and given a vertex gamma and a generator sigma, I put an edge between gamma and sigma times gamma labeled by, and the edges are labeled by the generator. So this edge from gamma to sigma gamma has the label sigma on it. So examples, if the group is the group of the integers, the additive group of the integers, and the generating set is plus minus 1, then the Kelly graph is an infinite path, infinite in both directions. Similarly for ZD, the Kelly graph with an appropriately chosen generating set, the Kelly graph is a d-dimensional square grid. And if we take, say, the free group, then on n generators, the Kelly graph is an infinite 2n regular tree. So this framework was the kick, of Kelly graphs is really just a broader context in which you can put all of these examples. There's some kind of, for every group gamma gives rise to this nice symmetric looking graph, which is called the Kelly graph. And we say that the gamma graph is a graph with edge labels in which every connected component is isomorphic to the Kelly graph. So we think of one of these Borel graphs with uncountably many connected components, and each connected component looks like a Kelly graph. So maybe each connected component is a regular tree or a d-dimensional grid or a path, something like that. Okay, so this is just the definition of the gamma graph again, and here's one very important example. This is given an arbitrary group gamma like this, we can construct a canonical instance of this, a Borel gamma graph, which is called the shift graph of gamma, as I'm going to denote it as sub gamma. Here's how it's defined. So first, I'm going to look at subsets of the group, and you can think of them alternatively as just their characteristic functions, so assignments of zeros and ones to the elements of the group. So given such a subset A and an element gamma, I let gamma times A be just the shift of A by gamma. So I look at all the elements alpha and A and I multiply them by gamma. So I shift, in other words, I shift this subset of gamma by this group element. And we're going to say that the set is aperiodic if it is different from all of its shifts. If gamma times A is not equal to A for every non-identity element gamma. So the shift graph S sub gamma is defined as follows. The vertices of the shift graph are the aperiodic sets, aperiodic subsets of gamma. And for every such aperiodic set A and the generator sigma, I put an edge between A and the shift of A by sigma. And it's labeled by this generator. So the reason why we need to look at aperiodic sets here is that this ensures that this is indeed a gamma graph, that every connected component is isomorphic to the Cayley graph of gamma. So for instance, because A is aperiodic means that A and sigma times A are different. So there are no loops in this graph. And but moreover, somehow this general assumption in fact guarantees that that every connected component is just a copy of the Cayley graph of gamma. Okay. So this is just a very concrete definition of a graph where every connected component looks like the Cayley graph, is isomorphic to the Cayley graph. So if in the case where the group is, I don't know, the free group, right, every component will be a regular tree. And these are, I should say that this is, on the one hand, this is essentially the only way we know how to construct nice examples of these gamma graphs for every group, for a given group gamma, if we don't know anything about it. And on the other hand, it's really somehow very important. So there are a lot of connections with dynamical systems here. So there is a reason why we want to consider things that are generated by groups somehow. In dynamical systems, ergodic theory or topological dynamics, which people study group actions, and somehow these shift graphs play a very, very important role. So now here's the theorem. That it turns out that continuous combinatorics, at least in the setting of gamma graphs, so these nice symmetric graphs, continuous combinatorics is exactly equivalent to deterministic, to having a deterministic local algorithm that runs in little log n rounds. So here's the theorem that is due to myself and Grebin, Jackson, Rojon, Sievert, and Vidnyansky independently. It says that for every LCL problem pi, the following two statements are equivalent. We can say, does the shift graph admit a continuous solution to pi? This is a continuous combinatorics problem. On the other hand, we can ask, look at the finite subgraphs of the Cayley graph. Can we solve the problem pi using a fast deterministic local algorithm? So these two things are equivalent to each other. Again, having a continuous coloring or continuous labeling that solves the problem on the shift graph is exactly the same as having a little log n round deterministic local algorithm that on finite subgraphs of the Cayley graph. So here, the direction from 2 to 1 is very similar to this, given a deterministic algorithm, you need to get this continuous solution. I kind of sketched to how you get a Borel solution. A similar argument really in this context can give a continuous solution as well. So the direction from 2 to 1 is not very difficult. The direction from 1 to 2 is hard. It's much more hard at least. It requires some non-trivial arguments, which I will not go into. Right, but this is kind of an interesting feature that what this argument shows is that given this continuous coloring, somehow you can extract out of it an efficient deterministic algorithm. And let me say that people have been, so this is an exact equivalence between two areas, and people have been studying these two independently of each other for different reasons and using different methods. So, for example, a salient example of this is the analysis in the case where the group is ZD. So, in other words, we just studied D-dimensional square grids. So then, there was work in continuous combinatorics by Gao, Jackson, Krohn, and Sievert, and in distributed combinatorics by Brandt et al. And they proved essentially the same results in these two different settings. And now we know by this theorem that there is a reason why the results parallel to each other, because they're actually equivalent. Okay. Now let me mention one more situation in which we have this exact equivalence between a distributed, between having an efficient distributed algorithm for a problem and having a corresponding result in descriptive combinatorics, which is this remarkable recent result of these authors. They consider problems on trees. So this is a more specific context that what we've been looking at before. There we looked at Cayley graphs of groups, right? And now we specifically look at trees. So we fix a constant delta, and an LCL problem pi, and then the following statements turned out to be equivalent. This problem has a bare measurable solution on graphs where every connected component is a delta regular tree. So remember, bare measurable means it's Borel except for a meager set, so except for a topologically small set, right? So it's approximately Borel in the sense that there is this topologically small set on which things can go wrong. Okay, so having such a topologically nice, bare measurable solution to a problem on Borel graphs where every connected component is a delta regular tree, this remarkably turns out to be equivalent to having a big O of log n round deterministic local algorithm that solves this problem on n vertex trees of maximum degree delta. Why is this surprising? Because so here, notice that the bound on the number of rounds for this deterministic algorithm is not little O of log n, but big O of log n. So this actually is a very different setup. In particular, you cannot even, if you want to go from bullet point 2 to 1, having such an algorithm, you want to use it to find a bare measurable solution, right? You cannot do it directly. Because you cannot just pretend or tell the vertices that they live in a finite graph the way we were doing it before when we were simulating little O of log n round algorithms. In big O of log n rounds, a vertex is guaranteed to find a leaf in the tree. So it can see that the tree is not delta regular, right? And conversely, if the tree is delta regular, then well, the vertex doesn't, the algorithm may require the vertex to go until it finds at least one leaf in the graph, right, before it decides to make, to do anything. So this isn't going to work if the graph happens to be delta regular and has no leaves, right? So this really is surprising that this big O of log n actually turns out to be somehow related to the thing. And both directions here are non-trivial. It's both going from 1 to 2 and from 2 to 1, but both require non-trivial work. So I think this is a really inspiring result that shows that we can probably push these ideas even further and look at the time complexities for local algorithms that do not obviously translate into the setting of Borel graphs, but maybe we can find some kind of clever ways to use them to produce descriptive results. Now to sort of finish or wrap up this talk, let me say a few words about open problems. And well, essentially, pretty much anything that I did not tell you about is an open problem. There are lots of open problems in the area. We're just scraping the surface of what lies there, what seems to be true of all of these connections between distributed computing and descriptive combinatorics. But here are some major problems in particular that you can ask. So we already know that there's one direction from you can go from distributed algorithms to descriptive results kind of generally. We know this connection with continuous combinatorics is essentially equivalent to deterministic distributed algorithms running in little O of log n rounds. But what about Borel combinatorics? This is one of the primary questions in descriptive from the descriptive complexity side. Is there a precise distributed algorithmic counterpart to the class of problems that admit Borel solutions? We don't know this. We don't know what this counterpart would be. And the same for measurable solutions, which also is important. So just to illustrate the situation that we're in now, on regular trees, here's what we know. As I mentioned, we know that the deterministic local algorithms running in little O of log n rounds, I'm dropping that for brevity. This is the same as having continuous solution, which of course is a stronger requirement than having a Borel solution. So problems that admit Borel solutions form a subclass, continuous solution, sorry, form a subclass of problems that admit Borel solutions. We know that there are problems that that can be solved by an efficient randomized local algorithm, but that do not have Borel solutions. These, in turn, as I mentioned, are included in the class of problems that have measurable solutions. And of course, having a measurable solution is a weaker condition than having a Borel solution. In fact, strictly weaker, at least on trees of sufficiently high degree. yeah, for example, a delta regular tree for delta at least 3 has a measurable delta coloring, as I mentioned a while ago, but it doesn't always have a Borel delta coloring. So this inclusion is strict. Actually, we know more. Some of the other inclusions here are also strict, and this also comes from this work. So the inclusion of continuous into Borel is strict. So there are problems on regular trees that can be solved in a Borel way, but not in a continuous way. There are problems that can be, what is even more surprising is that there are problems that admit, that can be solved by a randomized local algorithm. That cannot be solved by a randomized local algorithm, but can be solved in a Borel way. So that's why it's really mysterious what this class of problems that have Borel solutions really is in relation to the distributed algorithms world, because it strictly contains the problems that can be solved by a deterministic local algorithm, and it's incomparable with those that can be solved by a randomized local algorithm. Some problems belong to this class and not the other, and vice versa. And of course, this also shows that there are problems that have measurable solutions but cannot be solved by a randomized local algorithm. So this is what we know, and so we don't really understand how to precisely locate the Borel and measurable classes in the distributed complexity world. And on the other hand, all of this is for trees. This is a specific class of graphs, right? And different classes of graphs, even some of these distinctions are open. For instance, if we're working on square grids, or I guess graphs where every connected component is a square grid, it's Z to the D graphs in the terminology introduced a few slides earlier. We don't even know if we can distinguish Borel and measurable solutions, for example. So it's not known whether there are LCL problems that admit measurable solutions but not Borel solutions on grids. So this is another open question. Yeah, so let me finish with this slide that has a list of references to all of these results that I mentioned in this talk. You can, if you're interested in learning more, you can go and look at all of these. And all of these are preprints because, as you can see, the earliest date here is 2020. So this is a really recent work. And thank you very much for your attention.